Of course, we don't actually know the variances in two populations typically. Just like we don't know the variance in one population, we don't know the variance in two populations. So really what we want to do is turn this into what's called a two-sample t-test, which is much more common, which accounts for the fact that we don't actually know the variances. However, just like in the case of the one-sample t-test, we need to assume normality if we're not going to say that we know the variance. So now we have to assume that x follows a normal distribution and y follows a normal distribution. And each of those distributions is centered at some value, mu x or mu y. And of course, each of these distributions does have some variance. I just am not claiming anymore that I know what it is. Okay, so let me slightly change what I have here. I'm going to change what I have here only very slightly. Instead of sigma squared x and sigma squared y, I'm going to write s squared x and s squared y, where those are the two sample variances that I can calculate using my data. What is the reference distribution for this statistic, this T-statistic? Well, it's not technically going to be normal anymore. And it turns out that it's not technically a t-distribution either, but it's really close to one. So we can think of it as a t-distribution approximately with a certain degrees of freedom. What is this degrees of freedom? Well, it's estimated computationally using something called Satterthwaite's approximation. And if you use that, it's a function of the sample sizes and the variances. You get a certain number, and the reference distribution for this thing is approximately that t-distribution. That all sounds really complicated. But as long as your sample sizes are pretty big, you just use a normal distribution, which is centered at 0 and is between 2 and -2 with 95% probability, and that is typically good enough. Importantly, all I did here was plug in those two variances. So for this particular t-test, that I've done here, I'm using what's called the unpooled or Welch T-statistic. What did I have to assume here? I had to assume that I have independent samples from the population. I was supposed to assume that each of those populations was normal. I had to make that assumption. Okay. And then I just plugged in my estimates of the variance. If you're able to assume, though, that the variances are the same in each population, if that's a reasonable assumption to make, then things are a little bit simpler. So suppose I know that the variance is the same, and I'm willing to assume that. Okay? And suppose I have an estimate of that quantity, something like, I'll call it SP squared. Turns out that's for pooled, right? Then what I have is SP squared over NX plus SP squared over NY. I'll write out the equation for SP squared in a moment, but the point is, unlike SX squared and SY squared, SP squared is an estimate of the variance that takes into account both data sets, both the X's and the Y's. Okay, but if I'm going to do this, I may as well factor out the SP squared and take it out of the square root, and what I get is this. 1 over NX and 1 over NY, and the reference distribution for this turns out to exactly be a t-distribution with NX plus NY minus 2 degrees of freedom, but if NX and NY are pretty big, that looks exactly like a normal distribution for all practical purposes. How come this test statistic, which is the pooled t-statistic, how come this pooled test statistic, this pooled t-statistic, does exactly follow a normal t-distribution, whereas the unpooled Welch t-statistic only approximately follow the t-distribution? The reason is that this t-distribution comes from having something that's normal divided by square root of something that's chi-squared that follows this chi-square distribution. And this S does follow a chi-square distribution. But what I had before when I just plugged in the number was the sum of two S squares. And that doesn't follow officially a chi-square distribution. Technically, it doesn't follow one. And because of that, it was only approximately that this reference distribution followed a T. Looked like a T. But if I pool the variances, then this exactly works. Let's talk about this quantity, SP squared. What's going on here? Well, what does our data look like? We've got a bunch of x's, right? So here's a number line. Maybe, I don't know, our data goes from 1 to 70, something like that. I have a bunch of values for x. And I have a bunch of values for y. And perhaps the mean of the x values is something like 25, and the mean of the y values, the mean of the y values is something like 55. Okay, suppose that's the case. But I want to assume that these two histograms, these two sample distributions have the same variance, that the two populations had the same variance. So if I'm going to make that assumption, I may as well estimate that population variance that's the same in each group by taking into account how far each of these data points is from the mean in its own group. So what am I going to do? I'm going to take x1 and subtract from it the mean in the x group and square that. I'm going to take x2 and subtract from that the mean in the x group, etc. I'm going to take each of the values in the x group from x1 all the way up to nx, where nx is the sample size in the x group, subtract x bar and square it. But now I'm going to keep going. Let me take the first value in the y group and subtract y bar and square it. And let me take the second value in the y group, subtract y bar and square it. All the way up to the ny value, where ny is just the sample size in the y group, and square it. So now what I have is the sum of the differences between each value in my whole data set and the mean in their own group. And I'm going to take this whole thing and sort of divide by how many numbers there are. I'm sort of going to take the mean of these. If I were to just take the mean, I would divide by nx plus ny, because that's how many differences I have in this numerator. However, technically what I'm going to do is divide by nx plus ny minus 2, and this is the quantity that we call sp squared. Why is it nx plus ny minus 2? For all the same reasons that we discussed for using n minus 1 when this was just s squared in one group. I've used up two pieces of information, estimating x bar and y bar. If I start out with a total sample size of 200, two of those pieces of information have been used up. If I want it to be true that on average, the pooled variance is equal to the true variance, whatever that is, I need this quantity. I need that to be there. If I want this entire quantity to be bigger in order to reflect that I don't even know the means, I don't know what values I'm interested in differences from. If I want this entire thing to be bigger, one way to do that is to make the denominator smaller, and that's what that minus 2 does. This quantity here is called the pooled square, the sample variance. Let me actually say it. This quantity here is called the pooled sample variance, and we use it for the pooled t-test. It's appropriate when we think that it's fair to assume the variances are the same in each of the two populations. In the case of a t-test, we usually don't have to make that assumption. It's usually fine to go ahead and do the unpooled test or the Welch test. There's no reason not to, usually. However, as we start to talk about slightly more advanced or much more advanced parametric tests, it's going to turn out that this assumption that the variances are the same in each group is going to be more important. It's more often required. There's less often a really easy alternative to assuming that the variances are equal in each group. So this quantity, this sp squared, this pooled sample variance, is going to be something that we come back to and that makes sense anytime we want to assume the variance is the same in lots of different groups and come up with an estimate of that quantity.